Hello everyone, and welcome to this rather rainy afternoon in my Minecraft world. Back to ChatCraft. And today's topic is very interesting to my mind. It's from Cosmology, basically dealing with where the universe comes from and where it's going. Problem is, I am even further away from an expert on this topic than usually, and it is a fairly complex topic. So, I'm afraid I have to use notes for this, which means you might hear paper rustling at times. I don't know how much the microphone picks it up. So, yeah. This whole thing basically started back in the days when, well, part of it started when Einstein came up with his theory of general relativity. And, he basically worked out that time and space aren't really separate things. Now, that's not the way he phrased it, obviously, but that's one of the things you can take away from him, from general relativity, that sufficiently heavy objects can potentially curve space and time around them. And in his equations, he tried to work out basically how the curvature that was generated by certain things related to how heavy they were, in essence. This being pretty much a fairly rough understanding and a quite generalized version of what it was all about. But anyway, and in a sort of related thing, people back in the days used to assume that the universe was static. So it had always been basically as it is right now. It's sort of an eternal thing that just is and has always been. And that view caused certain issues. One quite important one, of course, is that if the universe is infinite in age and size, then we would expect if it's infinitely old, we would expect all the stars in the universe to have reached us by now. All the light from all of them should have arrived here at some point. And if it's also infinitely big, we would in addition expect that in every bit of the night sky where you don't see stars, there should be stars in between if you go far enough back, and the light of those should have reached us. So one of the problems is that we would expect the night sky to be completely illuminated at all times, which we don't. So along comes a guy called Edward Hubble, who the Hubble telescope is named after, so that's not a coincidence in any way. And he discovered that, in fact, everything we see, all the other galaxies we see through telescopes, they're all moving away from us. And, well, that seemed at first to support the idea that Earth is indeed the center of the universe, because if everything is moving away from us, then we should be at the center, right? And obviously that's not quite true. The way to think about this is if you for example take a balloon, like one of those, just a normal balloon, you could blow it up, but before blowing it up you just start drawing dots on it in a regular pattern. So let me just try and show that. You basically kind of just make a random pattern with dots on it. Well, not really random, some sort of regular pattern, in fact, something like this. And now when you start blowing up the balloon, these dots will all move away from each other, because the balloon is expanding, just like the universe is. And that means that in any of the galaxies, you expect to see the same thing. Any galaxy would see everything else moving away from it. And so how do we know that things are moving away from us? Well, that's due to a thing called the Doppler effect, which I can also demonstrate in a way right here. So let's say I put down these posts. And now I'm moving at a certain pace. Now I don't really have different speeds in Minecraft, so just assume you've got these posts and you're walking by them. And you see one post each second, because that's how fast you move. If you now move twice as fast, you will obviously see 2 posts per second. And if the posts were moving as well, that would change how many you see per second. So if you're moving at 1 post per second and they're moving at the same speed, if they're moving in the same direction, you're never actually going to see the posts. You're only going to see the one you're currently seeing. But because you're moving at the same speed in the same direction, it appears to you like they're not moving at all. If, however, they were moving in the opposite direction at the same speed, you would see them as moving twice as fast. And that's kind of what the Doppler effect is. If you're running past a wave, its apparent frequency changes depending on your speed, because the frequency is basically how many peak points go by you per second or something like that. And if you're moving in the same direction as the wave, it seems to be slower because you see less peaks per second, and if you're moving in the opposite direction, you see more peaks per second. That's basically the Doppler effect. And it applies to light as well, for different reasons, but the idea is exactly the same. So if you see light from a faraway galaxy, and you know roughly how, because of astrophysical observations, you know what wavelengths of light you expect, and you know they're shifted. So from that you can tell that things are moving away from you, because there has to be relative motion between you and the light source, because it's shifted towards the red spectrum. And so that tells you that things are moving away. And in order to work out that further things are moving away faster, which is another observation that Hubble made, you have a bit of a problem. Because you can work out the speed of the galaxy that's moving away from you. You can work out the speed by how much the wave is shifted, how much redshift there is. That tells you very precisely how fast the galaxy is going. But to work out the distance, that's quite complicated, because you don't really have the tools to do that. And triangulation, which you could use for medium-sized distances, I guess, on Earth, for example. You just you compare the angle you see a certain object under when you're moving. So if you see an object under a certain angle and under a certain different angle, if you move 2 meters to the right, you can work out how far away the object is. But the galaxies are so far away that that doesn't work. Just because you cannot measure accurately enough. In theory, it would work. If you had measurements which were massively accurate enough, then yes, you could use that to work out the distance, but you just can't measure it that well. So you're sort of stuck without that method, basically. So what else can you do? And there is a thing which we now know, another method of working out distance which does work. If you look at a light source, and you know how bright it is, you can tell how far away it is by basically how much of that energy arrives at a certain distance. Because you know that the light energy is going out in all directions, uniformly distributed, and by telling how much of that energy is still captured at a certain you know the distance, basically, because you can calculate how much energy is still left over at a distance, and if you know the leftover energy, you can calculate the distance backwards from that, if that makes sense to you. So if we can find a light source of fairly well-known energy in a distant galaxy, we can use that to sort of work out how far away that galaxy is. Now the problem is we need light sources of fairly well-known brightness, and that's a little problematic because we don't exactly know how bright things are that far away, because it's difficult to tell what exactly they are. It's not an unsolvable problem, but it's complicated. So that's why when Hubble worked out these things, he was off by a factor of 10, which is incredibly good considering the limitations that he had at the time. Those were freakishly good results, more than you would expect, really, but still the factor of 10 out is quite far out. As I said, it's better than you would really expect, but still not exactly perfect. And that's because he didn't really have any good standardized light source. He couldn't use those, basically. He didn't have any he could use. But now there are sources of light which we understand well enough to work out pretty precisely how bright they are. And they're called supernovas. And supernovas are basically exploding stars. Not all stars die in the same way, but supernovas are basically the most drastic, the largest cosmic events, maybe aside from the Big Bang, but they are huge. There is a general rule of thumb accepted under physicists that, just to give you an idea of how large numbers are connected to supernovas, however big you think they are, they're bigger. If you take a supernova at the distance of the Sun, so you're standing on Earth, there's a supernova at the center of the Sun, that is brighter to you than if you take a hydrogen bomb and detonate it on your eyeball. That's how bright supernovas are. They are ridiculously bright. They are among the largest events known to us ever. And especially, they are easily bright enough to see from vast distances. Now you might think supernovas, they must be super rare, right? And yes, you are correct. Supernovas are rare. They happen, I think, roughly once every 100 years per galaxy, so that's not very common. But the thing is, it doesn't really matter how, that they're that uncommon, because the universe is huge. The example I heard, or rather the illustration I heard, is if you go out at night, and you sort of make a ring with your thumb and your, what's index finger pointing? I don't know, the finger next to the thumb, whatever you call that. Just make a ring with these and point it at the sky, into a dark area of sky where you can't see a star there. In that area, you see, well, you don't see, but there are, and they are observable to telescopes, 100,000 galaxies. And in any given night, in that area in the sky which you hold up, basically, you would expect about 10 supernovas. So they are really rare, but the universe is gigantic. So large that there's really nothing else to compare it to. It's not like you can say it's as large as, because there is nothing else as large as. Not even close. The universe is so massive that even a really rare event like a supernova happens all the time. Nothing special, really. And you can use these to work out quite accurately how far away galaxies are, And that basically tells you that the further away a galaxy is, the faster it's moving away from us. And again, if you use the balloon example, and if you like, you can actually try, if you can measure it well enough, to actually do that yourself with a balloon. That will work. Like, that is actually that's just what you would expect in an ever-expanding universe. Using the balloon example, the further away something is, the faster it's bound to move relative to you, just from what you would expect. And that basically told us that indeed the universe is expanding, so it's not eternal and static, and that was rather problematic. Well, it wasn't problematic, but it showed us that the idea that the universe is static kind of been right. And then from that going on, well, rather, that was the first discovery that really changed how people saw the universe. And then, at a much later point, a far less basic observation was made. Like, what I've talked about so far isn't really basic, but the tools you need to make those discoveries aren't that advanced. At a later stage, it was discovered that what we would consider empty space, so if you take an area of space, universe, big space somewhere, you take an area, you take out all the matter, you take out all the radiation, all the waves, everything, nothing in it. Then that bit of empty space does have a mass. It's not actually as such empty, it weighs something. And that is due to quantum mechanical effects, which basically, quantum mechanics allow matter to spontaneously form, in a sense. So you can suddenly have matter where before there was none, because gravity can have negative energy. The point is, you would think matter is suddenly springing into existence that violates conservation of energy, right? Because matter is basically energy, so if we can have energy where before there was none, we must have somehow made energy. And that can't work. The thing is, gravitational energy can be negative. So, compensating that, you can have matter suddenly springing up, basically. Which is quite a cool effect. And it's not a purely theoretical thing. It's not something that quantum mechanics tells you could happen. It's something that does happen. It's been observed. For example, people actually got a Nobel Prize for this, or something related to this. If you take a proton, and we now know that protons consist of quarks. If you take the mass of all the quarks inside a proton, and you add up the mass of these, you only get about 10% of the total mass of a proton. The other 90% of the mass of a proton stem from the empty space inside the proton. Because in that empty space, virtual particles pop in and out of existence all the time, and fields start popping out and disappearing again from quantum mechanical effects from nothing. And these contribute 90% of the mass of a proton. So that tells us that empty space has a weight. And so you basically, scientists then looked at the universe, roughly estimating how big it is. You can do that quite well. And they looked at all the empty space and assumed, okay, so if that happens everywhere, roughly how much mass would we expect from that? And they arrived at a terrible number. It was massive. It was something, it had 120 orders of magnitude, basically. And that just couldn't be right. So these quantum mechanical effects obviously weren't that well understood yet. And basically all that ties in with the question of how the universe works, where it's going and where it's coming from. And to work out where the universe is going, we need to work out something called the shape of the universe. Or rather, the geometry of the universe. The problem is, the universe is, as I said, rather large. But it turns out that it would be possible that our general idea of space isn't really correct. Mostly because me as a mathematician in particular, I could imagine a space that's not conforming to the rules we would expect it to. Like parallel lines never meeting. In mathematics, you could easily have parallel lines that actually meet at some point. Or you could have parallel lines which don't have the same distance at all times, or something like that, depending on what you mean by parallel lines, of course. But it might be that the universe isn't a perfect Euclidean space. If that means anything to you, fine. If not, I'll get more into detail later. So basically there's three options for the universe. Firstly, it could be a closed universe. A closed universe, we would expect this to expand, and at some point the expansion would stop and reverse, and everything would collapse back in on itself. Which is, there was some sort of explosion which caused the universe, which we can still detect, so everything's blowing apart. But gravity would also pull things together, so we would expect eventually, if the universe is closed, we would expect the gravitational pull to be stronger than the force of the explosion blasting it all apart, and it would slow down the explosion and everything would collapse gravitationally in on itself again. So everything would crunch back together, which would be a consequence of the universe being closed. The universe could also be open. In an open universe, different geometry, it's kind of difficult to explain and pretty much impossible to draw. But in an open universe, you would basically expect the expansion to increase all the time. So the universe expands and accelerates that expansion all the time and never stops. And the third option is kind of the middle option. It's a flat universe. It's Euclidean, it expands all the time, but the rate of expansion slows down. But it never quite hit zero. It's just getting slower and slower and slower. So and that the question which of these universes we live in actually has a lot to do with how heavy the universe is. Of course, it's not entirely easy to weigh the universe, but it's possible. And since this is a large topic and going to take more than one episode, if you want to know how physicists manage to weigh the universe, tune in next time for ChatCraft. I'll see you then. Bye bye.